We are in 1.5. We're going to talk about inverse functions today. So what are inverse functions? These are functions that quote unquote undo each other. So it's very much like the idea of, 2 steps forward, 2 steps backward, you end up where you started. So let's talk about what that means mathematically. What would be the inverse or the undoing of add 3? Well, that would be the idea of subtract 3. And you all understand that idea. Okay, so in the language of functions, what add 3 means is that you take an input and then you add 3. So the inverse function, and we write f inverse of x with this -1 exponent here, is, okay, now take your number and your input, subtract 3. And these would undo each other. So what is the inverse of x squared? Well, what is the inverse or the opposite of squaring? That would be the square root of x. And okay, that's, yeah. All right, so if your function is a little bit too difficult to find an inverse with, then you can always follow these steps to do it algebraically. And when you do these 2 steps, what you're doing when you switch the x and y is and solving for the new y is you're reversing every single operation on the x. And that's why it works. So I'm going to do that for this example here. Suppose we have x cubed minus 3. Let's switch x and y. So now x is y cubed minus 3. And now I'm going to solve for this new output y. So I add 3 to both sides, and then I take the cube root of each side, and I get the cube root of x plus 3. That is my inverse. Okay, and now there's a second example here. In this second example, y equals 3 over x minus 1. The first step I'm going to do is switch my x and y. X equals 3 over y minus 1. Now let's clear denominators by multiplying both sides by y minus 1. That will cancel the denominator on the right, and when I distribute the x on the left, I get xy minus x equals 3. Let's add x to both sides, and then divide by x, and we get 3 plus x over x. So that's my inverse here, G inverse. All right. So how do you know that 2 things are, so how can you verify that this is right? Maybe we want to check and make sure it's right. Then what happens is if you go 2 steps forward and 2 steps backward, then nothing happens. So this means that your input and your output are the same. And so if you compose these 2 functions, so do the inverse and then do the original, or do the original and then do the inverse, what happens to x? What happens to x? Nothing. You get out x. Your input and your output are the same. Nothing changed in the input. It didn't randomly, magically convert to 1. It just stayed the same value, so it is x. All right, so now we're going to work on those same 2 examples again. How do I verify that f of f inverse of x is, or f and f inverse are truly inverses? You're going to compose these functions. All right, now remember, f inverse of x was the cube root of x plus 3. All right, double check. Yes. All right, so now I'm going to take f inverse, and that's going to be, I'm going to put that into this x and f. So I have the cube root of x plus 3 cubed minus 3. These cube root and cube cancel, and I get x plus 3 minus 3, and that is x. That's what I'm supposed to get, nothing. Input and output same. All right, now let's do f inverse of f. Okay, so now into my cube root function, I'm going to replace the x with x cubed minus 3. Now my minus 3 and plus 3 cancel, and I get the cube root of x cubed, which is the nice, beautiful x. I'm going to leave this for you to do. So you can pause it and work on that one now. Compose G and G inverse. We got G inverse on the previous page. And then G inverse and G, and make sure you get x. This is a algebraically not quite so fun, but I want to check and see that you can do these algebra operations, and then I'll work with you one-on-one if you can't get that right. Okay, so once you're done with that, let's do inverses graphically. For the picture of the inverse and its original function, graphically, these are symmetric over the line y equals x. And again, that's that when you switch x and y, you get a lot of interesting things, and one of that is the symmetry with y equals x. So when is the inverse of a function 2? It's when the inverse passes a vertical line test. So in order for the inverse to pass a vertical line test, the function itself must pass a horizontal line test. Because remember, we're switching x and y. And so in order to hit that vertical line only once, the horizontal line in the original equation must only hit the function once. Okay, so let's do this example here. I had x cubed minus 3 as my original x graph, or f graph. And I'm just going to plot a couple of points here. This is my x cubed graph. The 0 part is where it flattens. And then my inverse was cube root of x plus 3. Now, I'm very familiar with how that graph works. The cube root graph, I call it the walk like an Egyptian graph because it looks like your arms look in that funny dance. Okay, and so that's your f inverse graph. And look, the line y equals x is that perfect 45-degree angled line. This is the line y equals x. And notice the beautiful symmetry that happens there. I'm not going to actually make you graph this one. That's a little too much for at this point. Okay, last thing. Sometimes when you have a function, we don't pass a horizontal line test, but we still want to figure out the inverse. And I sort of glossed over this example before, but we talked about x squared, and I said that shouldn't the inverse be square root of x? And yes, that is the inverse. The problem is that x squared does not pass a horizontal line test. This is the graph of x squared, and so we failed the horizontal line test. This failed. Okay, so how can I make this so that I pass the horizontal line test? Well, I restrict the domain. Okay, so I don't let f be just the function x squared. It's only x squared if x is greater than or equal to 0. And so in this new definition, f of x equals x squared for x only greater than or equal to 0, now when you graph this, we only get the right half of the parabola. We're at the right half of the parabola. And now when you graph the inverse, let me just give you a couple of points here. So we get 0, 0, 1, 1, 2, 4, 3, 9, right? So now when you graph the inverse, you can switch these x and y coordinates. So 0, 0 is still 0, 0. 1, 1 is still 1, 1. But now 2, 4 is 4, 2. So 4, 2 would be here. And this is that square root graph. And notice this, if we're familiar, this is y equals square root of x. We're familiar with that graph. And if you only use the right half of the parabola, we're symmetric over the line y equals x. And so if f of x is a different function, not x squared. So for f of x, it's x squared, comma, x has to be greater than or equal to 0, then f inverse is square root of x. The domain of this is 0 to infinity by definition, and so is the range. And that's also your domain and range in the inverse. And it works nicely that way. Okay, that's all I have.